So there's a couple rearrangements we can have of our ideal gas law that gives us some more information. So I thought I'd just highlight those a little bit. First of all, we can find out the density of a gas because remember, density is equal to mass over volume. And so if we use the fact that density is mass over volume, we can substitute this into the ideal gas law by solving for what V is equal to. Because remember, volume is V. And so if we do that with the ideal gas law, then we could put that back into the density equation. So I could put basically this in here. So mass would be equal to nRT over P, which has way too many things on the top and the bottom. And if you remember, when you have something here on the bottom that's on the bottom of something else, that's the same thing as having it up here on top. So that's where this P comes from, up here. But what that means is that we could say density is equal to mass times pressure over nRT. Well, if you recall, when we used molar mass is defined as mass per mole. So grams per mole. And so what we can say is this right here, the mass and the N, is the same thing as molar mass. So we're going to give that another value. We're going to call that M, a big fancy M with a slight slant to it, but we'll call it M. So we could say in total then that density is equal to molar mass times pressure over R times T. And where is that useful? Well, here's an example problem. What's the density of O2 gas at standard temperature pressure? Remember, STP means 273.15 Kelvin, in other words, 0 degrees Celsius and 1 atm. We can also figure out what the molar mass is of O2, and that gives us this value up here. So density would be equal to 32, because that's a molar mass, times 1 atm over our R constant times 273.15. Just plug and chug there, solve that. The density would be about 1.427 grams per liter. Now, when we're talking about gases, we talk about grams per liter, not per milliliter. So that is one thing I want you to make sure of. Remember, liter comes from right there. And so that unit is there if you check it out. Okay, so the same way we just said that mass is how many grams per mole we have, and that's the same thing as saying grams over N in terms of gas, right? Because N is the same thing as moles. We could say that this big M times number of moles is equal to grams, okay? Well, if that's true, I can solve for N and say that N is grams over big M. And then we can substitute this M right here into PV equals nRT. And essentially what you end up with is that PV is equal to grams over molar mass times RT. Or if we solve for this M or the molar mass, we can say that the molar mass is equal to grams times RT over PV. Now, some of you all may want to actually run through that math yourself, because I just did that really fast. And some of you may just want to take the final equation and use it. Either one of those is totally fine. For me, it helps me to know where equations come from, at least once, to know that they're real, right? But we can essentially take this last value right here and use this to determine the molar mass of an unknown gas, which will also somewhat give us a clue of what our gas may be. So, for example, if we need to calculate the molar mass of a gas and it weighs 1.78 grams at 1.25 atms and at 150 degrees Celsius and occupies a volume of 1.3 liters. So you get a tank and you need to know what it is. Well, we can use that equation that we just used from the previous page, and basically plug and chug things in, keeping in mind that you still need to convert to Kelvin. So we do that at 1.78 times our R value times temperature over pressure times volume will give us the molar mass. Since that's 38, it may very well be fluorine. So because each of these has a molar mass of 19.0 grams per mole, and there's 2 of them, so it may very well be that formula. Okay. But probably one of the more important things that we need to still deal with is something called the Daltons Law of partial pressures. Well, so this actually is not a difficult concept. All that this is saying is, hey, when you add 2 things together, they equal the total. Like literally, that's all it's saying. Because when you have a partial pressure of, say, oxygen and hydrogen and nitrogen, they all add together to equal the total pressure, which means that you can tell how much there is of each of them because they're basically a fraction of the amount of the total. But it also means that if you're trying to figure out the pressure of the total amount, we can simply add together those values. So for an example, if you have H2 and O2 in a container, they have 0.1 atm and 0.98 atm of partial pressures respectively. What that means is the first number goes with the first thing here, and the second number goes with the second thing here. If you've ever heard that respectively comment, and it asks what's the total pressure of the gas, you add the 2 numbers together. Now, if you wanted to figure out what the volume was that was due to just this guy, you can do that by using PV equals nRT. Same thing with this guy. And I'm pretty sure that you all could figure out if you're given the total pressure and say that you're trying to figure out what the partial pressure is. In other words, you're given this value and you need to figure out what this value is, you can figure that out because the 2 things equal the big thing, right? And then if you need to do something with that value to find volume or whatever it may be, you can do that as well. So a lot of these problems are now going to focus on what do you have, where do you need to go with it, and using different equations to get where you need to get. Speaking of which, let's move into stoichiometry of gases. Guess what? We've done it before with mass, we've done it with volume and liquids. We can also do stoichiometry with gases. The only difference is that we need to use PV equals nRT to go from whatever pressure, volume, temperature, whatever information we're given in order to determine the number of moles that we have. Or perhaps we have the number of moles here and need to figure out what the pressure, temperature, or volume is of that gas. And so we can go in that direction as well. You have to use what you're given to figure out where are we starting, where are we going. You may start in a liquid and end up going up to a gas. It just depends on what you're doing. So let's try. So here's the example. You're using propane gas, and that combusts in the presence of O2 to form CO2 and H2O. If you're using 0.213 grams of protein, and you burn that at 1 atmosphere of pressure and at 27 degrees Celsius, what's the volume of CO2 gas released? So the first thing we have to do, like always, is figure out what our balanced equation is, which is exactly what I've done here. And then you need to figure out what do you have, where are you going, that type of thing. So we start with grams of C3H8. We need to convert that to moles of C3H8. That will then go to moles of CO2 and finally into volume of CO2. So that's what we're asked for. What is the final volume of CO2 that we have here? So we need to start with the molar mass of C3H8 because that's how we get to moles. So I calculated that here. And the other thing we need to know is how much is this temperature in Kelvin? Now, if you forgot to do that right now, that's okay. You can do it later. No big deal. Okay, so we're starting with 0.213 grams of C3H8. I convert that into moles of C3H8. And then I still use my balanced equation to determine how many moles of CO2 I have. This is a very important step, guys. You need to make sure that you're in the moles of the right thing before you go and calculate anything else. So make sure that you've actually gotten to CO2 before you convert that to a volume of CO2. Because otherwise you're finding the volume of the thing you started with, not the thing you end with, right? So we have this many moles of CO2. Now we take that value along with what we're given in the problem and simply find how many liters we have. So we've got 1 ATM. We're just going to use this. This, by the way, is just PV equals nRT, our ideal gas law. So we find that we have 1 ATM. This is how many moles we just figured out from this calculation above. Our gas constant's still there. We've got 300 Kelvin. Solve for V, and you find how many liters you have. Now keep in mind that this is liters, and also keep in mind we had a little bit of grams here. So that was not very big. That still gave you 357 milliliters of CO2 gas, which is quite a bit. Think your way through that in the end and go, does this make sense? Well, it does make sense that that's a huge amount or a larger amount considering that this is a gas. Every problem like this is a little bit different. You do have to think your way through these. So you certainly want to practice. Thank you.